Out at sea, beneath the steel deck of a cargo vessel, there exists an invisible system more fragile than the hull that protects it. It's not a fuel circuit or a navigation module. It's a floating aquarium, engineered not for display, but for survival. Inside, a giant fish breathes in silence, held not by nets or walls, but by the exact calibration of temperature, oxygen, and pressure. Moving hundreds of adult bluefin tuna across the ocean isn't just about transport. It's about recreating life conditions inside a mobile, industrial shell, in constant motion. Each tank becomes a marine biome in transit, a container where hydraulic load balancing must work in harmony with biological stability. It's not enough to move water. The system must regulate it, distribute it, oxygenate it with millimetric precision. Inside these modules, laminar flow paddles generate continuous water currents, mimicking the natural resistance these fish encounter in the wild. The goal isn't just to keep them alive, but to keep them calm, responsive, and injury-free. Water can't stagnate. Forces can't accumulate. The tank must breathe with them. What makes this challenge unique is its dual nature. It's mechanical on the outside, pumps, valves, dampers, reinforcement rings, but it's biochemical on the inside. A single lapse in oxygen saturation, a momentary imbalance in ammonia diffusion, and the entire operation collapses, not with a loud alarm, but in silence, as a chain reaction of stress, suffocation, and mass mortality begins. The failure isn't always visible. It's not about pressure gauges or tank temperature. It's about how well the dissolved oxygen is distributed, second by second, in an environment under constant agitation. This is where maritime engineering meets the biology of aquatic life. The same principles used in submarine ballast tanks, which adapt to pressure shifts within milliseconds, now inform the way live fish transport modules are designed. Load cells measure water displacement. Microprocessors regulate flow direction. In extreme weather, the system compensates for vessel tilt by adjusting internal currents, protecting not the ship, but the life inside its walls. In essence, it's a synchronized dance between gravity, inertia, and breath. There's a question that lingers in the silence of these voyages. If submarines respond instantly to depth changes, why don't we recalibrate live fish tanks every nautical mile? The truth is, some companies already do. And that's where the future lies. Because transporting high-value fish across the ocean is no longer just logistics. It's marine biology in motion. And every kilometer traveled is a test, not of fuel efficiency or engine power, but of our ability to engineer life support in one of the harshest environments on Earth. Next, we'll dive deeper into a failure that often goes unseen, a flaw that starts with oxygen and ends with invisible loss. Oxygen is the invisible currency of live fish transport, but unlike fuel or weight, it doesn't follow predictable lines. It moves in eddies, it dissipates with temperature, and it pools, sometimes fatally, in the wrong places. Most systems use single-point sensors to monitor dissolved oxygen, reading conditions from one stable zone in the tank. On paper, levels are acceptable, but the periphery tells another story. In areas where circulation drops or bubbles fail to rise uniformly, hypoxic pockets form, slowly and quietly. These zones do not trigger alarms. They only reveal themselves when fish start floating belly up. It's a failure of spatial awareness, a logistical blind spot in a three-dimensional system. Water might seem uniform, but its chemistry isn't. When movement isn't synchronized across the tank, microenvironments emerge. Some rich in oxygen, others depleted by respiration and waste. Traditional monitoring assumes homogeneity, but biology operates on gradients. That's why new systems now incorporate multi-zone oxygen mapping, using inline microbubble diffusers. Borrowed from hydroponic agriculture, this technology disperses oxygen-rich bubbles across the tank's entire volume, not just near intakes or central currents. The change isn't theoretical. When applied on transoceanic routes exceeding 72 hours, these dynamic aeration systems reduced instances of fish asphyxiation, and ammonia shock by 43%. In other words, nearly half of the biological casualties could be prevented, not by adding more oxygen, but by distributing it intelligently. Oxygen, in this context, is not a quantity, it's a pattern. The goal isn't saturation, it's circulation. To achieve that, the tank must act like a living lung, breathing, mixing, equalizing. A case from Japan illustrates the shift. A seafood exporter specializing in high-value tuna shipments began testing sensor arrays placed at multiple points throughout the transport modules. Alongside these, micro-bubble generators were installed, each calibrated to respond dynamically to real-time data. The result? 8 consecutive voyages without a single mass mortality event. The fish arrived alive, intact, and unstressed. A triumph of logistics through distributed intelligence. It leads to a simple but sobering insight. If your oxygen map looks like a flat line, you're not transporting live fish. You're just pushing water across the sea, hoping the biology keeps up. But in this industry, hope isn't a strategy. Precision is. And every breath counts. Inside a transport module filled with thousands of liters of seawater, mass doesn't just sit. It moves. And when that mass is a 250-kilogram fish, moving with muscle-driven bursts of speed, it creates a rotational force that is far from negligible. Each tail flick adds torque to the system. Each evasive spin adds momentum. In a confined volume of water, motion multiplies. The result is internal turbulence that stresses not only the animal, but the structure meant to contain it. Most tanks are engineered to withstand external pressures, wave impacts, deck vibrations, loading shifts. But inside, the challenge is different. Fish generate spontaneous torque, loads that ripple through the liquid medium, bouncing off walls, converging at corners, and amplifying as they go. It's a mechanical ballet with no choreography. Without mitigation, this chaos leads to injuries, not just to the fish, but to the integrity of the tank. The cargo becomes a source of destabilization. To address this, engineers turned to offshore oil platforms, structures designed to resist violent wave energy in deep ocean conditions. Borrowing from their wave-dampening technology, new fish transport tanks now incorporate anti-torsion rings and shock-damping liners. These inner rings absorb rotational forces, reducing the transfer of sudden torque through the tank's fluid. Meanwhile, flexible dampers embedded in the lining cushion impacts, protecting the fish from the very walls that surround them. The results are measurable. In a study conducted along a 5,000-kilometer Pacific shipping circuit, the application of kinetic dampers led to a 51% reduction in lesion rates among high-mass tuna. These aren't minor abrasions. They're injuries that affect meat quality, survival, and certification. By managing motion at the biomechanical level, the entire logistics chain gains reliability, from ship to shore. A company in Chile took this further. After retrofitting its fleet with damped transport modules, it not only reduced mortality, but achieved compliance with stricter animal welfare standards required by new markets. The upgrade didn't just protect the fish, it expanded their reach. What began as an internal structural adaptation turned into a competitive advantage, born from understanding how motion behaves inside liquid systems. Because in live aquatic logistics, mass is not a passive variable. It's an active, rotating force. A 250-kilogram fish doesn't just move, it punches. And if the tank isn't ready to absorb that punch, the consequences resonate far beyond the waterline. Curious about tech that moves the impossible? Check the pinned comment. Transporting high-value live fish across oceans isn't a matter of luxury or spectacle. It's a necessity forged by global demand, ecological limits, and technological ambition. But behind every successful voyage lies a quiet transformation, the reinvention of freight as biology. For decades, cold chain transport was defined by one principle: temperature stability. It was a race against spoilage, managed through insulation, refrigeration, and speed. But live aquatic logistics breaks that mold. Here, the cargo is not a passive object, but an active organism, breathing, swimming, reacting, and that changes everything. When we speak of transporting a 250-kilogram tuna, we're not talking about weight. We're talking about mass in motion, reflexes under stress, and biological responses to an engineered environment. These fish are not frozen. They're alive, alert, and sensitive to fluctuations in pressure, oxygen, light, and vibration. This turns every container into a microcosm, a closed system that must simulate nature while shielding its occupants from its own artificial constraints. It's here that agricultural engineering makes an unexpected crossover. In the fields, precision seed drills are designed to deposit seeds with millimeter accuracy while traversing rugged, irregular terrain. To protect the fragile seed metering systems, engineers developed advanced suspension technologies that isolate mechanical components from ground impact. Those same principles, motion damping, vibration absorption, dynamic compensation, are now being adapted for marine logistics. The containers carrying live fish across oceans now feature miniaturized dampers and suspension layers, designed to absorb kinetic energy caused by ship motion or animal panic. What once protected seedlings in soil now protects gills in saltwater. But engineering hardware is only part of the evolution. Increasingly, cold chain transport is embracing biofeedback, the ability to interpret the internal states of the living cargo and adjust environmental parameters in real time. In Norway, a startup revolutionized this field by integrating biometric monitoring systems into their fish transport modules. Sensors embedded within the tanks measure micro variations in movement, gill rate, and group cohesion. These aren't just mechanical signals. They're signs of stress, adaptation, or deterioration, the biological equivalents of red flags in a control room. With enough data, these systems begin to act almost like an autopilot. If fish behavior indicates rising stress levels, the system can modify internal flow patterns, reduce light exposure, or activate localized aeration zones. In one case, the system detected erratic schooling patterns consistent with low dissolved oxygen. Well before any traditional sensor would have sounded an alarm, the correction was applied autonomously, stabilizing the environment and preventing cascade mortality. The fish, in effect, had spoken, and the tank had listened. This interplay between machine and biology is more than innovation. It's adaptation, the conscious reshaping of technology around life. Cold chain logistics becomes, in this context, a form of managed aquaculture in motion. No longer a passive supply chain, it is an active extension of the production environment, with all the complexity that entails. The goal is not just to arrive, it's to arrive intact, with life signs unaltered by the journey. From a logistics standpoint, this changes the entire calculation. Transport time, traditionally the dominant variable, now shares priority with environmental stability. Routes are chosen not only for distance or weather, but for how they affect vessel stability and module performance. Crew training now includes elements of marine biology. Software engineers work alongside fish behaviorists. This is logistics redefined. A multidisciplinary orchestration where biology, mechanics, data science, and maritime law intersect, and the benefits ripple outward. Improved survivability rates mean less loss, higher quality, and access to premium markets. Healthier fish reduce the need for chemical intervention or emergency reprocessing. Moreover, welfare metrics are increasingly tied to certification and sustainability frameworks. A company that can prove its fish arrive healthy, unstressed, and unharmed gains not just economic leverage, but reputational capital in a market that values transparency and ethical practice. It's tempting to view these systems as niche innovations, tailored for a small sector of high-value seafood, but they signal something deeper, a shift in how we define logistics in the age of living cargo. Whether it's ornamental fish, marine invertebrates, or live aquatic produce for restocking natural reserves, the principles remain the same. Transport as biological management, not mechanical relocation. Looking ahead, the same intelligence that now powers live fish transport may expand to other forms of sensitive cargo, fresh produce with microclimate needs, probiotic cultures that require real-time pH balancing. Even vaccines and biological materials with live components could benefit from systems that adjust to the cargo's internal state, not just the container's external parameters. The next generation of cold chain transport will not be measured only by how cold it keeps the cargo, but by how accurately it maintains life conditions. Refrigeration will become part of a broader ecosystem of sensory feedback, adaptive control, and biological interface. The tank, the container, the crate, each will function more like a life support chamber than a storage unit. Because the future of freight is not passive. It is intelligent, responsive, and biologically aware. And it began, silently, with the question, how do you move a breathing animal across an unforgiving ocean without letting it know it's being moved at all? That's what this industry is achieving, not through spectacle, but through synchronization. Not through brute force, but through insight, through engineering that doesn't overpower nature, but moves with it, calibrates around it and listens to it, even in the middle of the sea.